This is lesson 510 on inverse of a matrix. Now before we get to talking about matrices, I want to take a step back talking about scalar values. Remember, scalars are just plain old regular numbers. So scalar is what we call just 5 or square root of 2 or negative pi. Those are all scalar values. So single numbers, not collections of numbers like matrices or you may have heard about vectors before. I want to take a step back to talk about scalars to introduce an idea, well not introduce, but to explain an idea about a simple concept that we've seen and we know, and then translate it over to what's going on with matrices. So when we've been working with scalar values, we have talked about two different ideas, even if we haven't called them these ideas directly. We have talked about what we call identities and inverses. For scalars, for our regular real numbers, the additive identity is 0. What we mean by that is if I add 0 to any order, it doesn't change anything. I get the same number back. Similarly, the multiplicative identity is going to be 1. If I multiply 1 by anything, it doesn't change anything. I get just the plain old number back. So an identity, if we add it or if we multiply by it, it doesn't change anything. Now an inverse, that is going to be something that we add or multiply by to arrive at the corresponding identity. So for example, the additive inverse of some number is just going to be negative that number. So the additive inverse of 4 is negative 4, because when I add those two numbers together, I arrive at the additive identity, 0. Similarly, for the multiplicative inverse, it's just going to be the reciprocal of some number. If I take 1/2 and multiply it by 2, or 2 times 1/2, I arrive at 1, the multiplicative identity. So an identity, when we add or multiply, when we apply the corresponding operation, it doesn't actually change anything. The inverse, given a particular number, its inverse is going to have us arrive at the corresponding identity. The additive inverse, when we add it to a number, we arrive at the additive identity. The multiplicative inverse for a number, when we multiply by it, we're going to get the multiplicative identity back. So let's take these two ideas of identities and inverses and talk about them in terms of our matrices. The identity matrix, so the only identity that, or rather the only operation that we're really going to focus on here is multiplication. If we think about it, we can figure out what the additive identity and additive inverse would be for a matrix. What's going to be the matrix that if we add that matrix to another matrix that it doesn't change anything? It's the matrix with all zeros. So the additive inverse of a matrix then would just be the original matrix times -1. That works exactly the same way as it did with scalar inverses, scalar additive inverses, so we're not going to focus on that. The more interesting case is when things are different from scalars, and we've seen that multiplication with matrices is quite different. So we're going to focus just on the multiplicative identity and the multiplicative inverse here. So if we ever talk about the identity matrix, we're talking about the multiplicative identity. The multiplicative identity for a matrix, it's going to be the square matrix where we have 1s along the diagonal and 0s everywhere else. So here I've given the examples of a 2x2 identity matrix and a 3x3 identity matrix. And we're always going to make the identity matrix a square matrix. So you can try this out, take any matrix you like. When we multiply it by the corresponding, the appropriately sized identity matrix, we're going to get the exact same matrix back. So we're going to use I to denote this identity matrix, and as we just stated, when we multiply a matrix by the appropriately sized identity, nothing changes. We arrive back at the same matrix. So we've talked about matrix identity. Given the setup that we did for scalars, we're probably going to be talking about the inverse of a matrix now. So recall, what was the additive inverse? The additive inverse given a number, is going to be the number that when we add it to the original number, we get 0. What was the multiplicative inverse? Is the number that when we multiply a given number by it, we get 1, the multiplicative identity back. So here, the matrix inverse, or the inverse of a matrix, given a particular matrix, its inverse is going to be the matrix that when we multiply those two matrices together, we get the identity back. We get the identity matrix back. So the inverse of some matrix A, we denote it A to the minus 1. Now, we don't necessarily mean 1 over A here. So we do not mean that we're taking the reciprocal of each entry here. So be aware of that. A to the minus 1, actually, I guess technically you could say that there is some relationship with reciprocal there, but that's not really what we mean here. Minus 1 in this case means that we're dealing with an inverse. So much in the same way that the reciprocal was the multiplicative inverse of a scalar value, here A to the minus 1 is the inverse of A. So when we multiply A and A inverse, doesn't matter which order in this case, that's something interesting. Remember, generally the order of multiplication matters with matrices, but here when we multiply a matrix by its inverse, it doesn't matter the order in which we multiply it, we're going to get the identity back. For our drill problems, we are going to focus on finding the inverse of 2 by 2 matrices. Now, if you noticed back in the introduction of the idea of the inverse of a matrix, we had this interesting phrase there, if the matrix exists. Not every matrix is going to have an inverse. The matrices that will not have an inverse are matrices whose determinant is 0. So notice here we've given a formula for the inverse of a 2 by 2 matrix. Notice that we multiply by the scalar value 1 over AD minus BC. I hope that AD minus BC looks familiar. That is the determinant of the original matrix. So if the determinant is 0, then 1 over 0, that's undefined. We can't do that. So only matrices with non-zero determinant are going to have an inverse. So for a 2 by 2 matrix, here's the formula. We're going to find the determinant. We're going to switch the order of some of our entries. We're going to switch around our A and our D entries and then negate our C and B entries. Then we're going to multiply it by the reciprocal of the determinant. So a few steps here, but we're always going to do the same thing. Switch A and D, change the sign of B and C, and then multiply each of those by the reciprocal of the determinant. So we do have to find the determinant, but for a 2 by 2 matrix, that's pretty easy, that's pretty simple. So no big deal, but we do have a couple of steps that we have to remember. So we're going to take a look at a couple of quick examples of finding the inverse of a 2 by 2 matrix, and we'll look at one example actually showing that, yes, sure enough, this is in fact the inverse. And we'll also take a look at how to find the inverse of a 3 by 3 matrix. Now, there are actually a couple of common ways to find the inverse of a matrix. We're going to look at one technique. It's actually quite a bit different from the formula that we've seen here, but it actually extends to larger and larger square matrices. So two quick examples for a 2 by 2 matrix, and then a longer application example looking at how to find the inverse of a 3 by 3 matrix. Okay, so we're asked to find the inverse of this 2 by 2 matrix. So remember, our formula for the inverse is going to be 1 over the determinant of the original matrix times we switch these two entries here, and then these two we change the sign. So the very first thing we need to do is find the determinant. So the determinant of 4, negative 2, 3, 1, so that's going to be 4 times 1, so 4, minus 3 times negative 2, so minus negative 6, plus 6, that's going to be 10. Okay, so we're going to multiply by 1 over 10. We're going to multiply the matrix where, once again, we're going to switch these two entries. So this becomes a 1, this becomes a 4. And then we're simply going to change the signs of these two. So negative 2 becomes positive 2, 3 becomes negative 3. So our inverse then is the final product after we multiply multiply by 1/10. So 1 times 1/10, that's 1/10. 2 times 1/10, that's going to be 1/5. Negative 3 times 1/10, that'll be negative 3/10. And then 4 times 1/10, that will be 2/5. So here's our final answer. All right, let's check this real quick. This is not something I would expect you to do for the drill, but just to show that, sure enough, this is the inverse. So let's take our original function, our original matrix, 4, -2, 3, 1, and multiply it by the inverse that we just found, or what we're claiming is the inverse. So negative 3/10 and 2/5. Alright, so remember, multiplying a 2 by 2 matrix, we take this row and this column first. So let's see here. So that's going to be 4 times 1/10. That's going to be 2/5 plus -2 times -3/10. So that's going to be, let's see here. That's going to be -2, so -6, so positive 6/10, so 3/10, 3/5. There we go. All right, so for our next entry, this row, this column, 4 times 5, that's going to be 4/5, and then -2 times 2/5, that'll be plus -4/5. All right. Second row, let's see if I can do this any better. So this row and this column, 3 times 1/10, that will be 3/10, plus 1 times -3/10, so minus 3/10. And last but not least, second row, second column, 3 times 1/5, that's going to be 3/5, plus 1 times 2/5, so 2/5. If we take a look at this, add up everything, 2/5 plus 3/5, that's 5/5, or 1. 4/5 minus 4/5, that's 0. 3/10 minus 3/10 is 0. And 3/5 plus 2/5 is 1. So sure enough, this is our inverse. Now I claim, we're not going to go through the details right now, but if you switched the order, so if you took the inverse first and multiplied that by the original, you're going to get the same thing. So I'm going to write it out here. Challenge you, take a moment, sit down, think through this. You're going to see that sure enough, you do get the exact same thing back. You do get the identity matrix back. So remember that this is not true in general. When we take the product of two matrices, if we change the order in general, we're going to expect to get something back. When we're dealing with a matrix and its inverse, though, that's one of the few exceptions where we will get the same thing back regardless of the order in which we multiply them. So this matrix, here's its inverse because their product gives us the identity back. So here's our final answer in this case. So once again, I won't ask you to check this on the drill, but I would encourage you, first few that you try, go ahead and do it just to, I don't know, to kind of satisfy, convince yourself that yes, this is in fact going to give us the inverse, so that when I multiply them, I get the identity back. So let's take another example, take a quick look at finding the inverse of a 2 by 2 matrix. All right, one more. So find the inverse of this matrix. So the first thing we need to do is to find the determinant. So the determinant is going to be -1 times -3, so +3, minus -2 times 5, so -10. So 3 minus -10, that's going to be 13. So our inverse is going to be 1/13 times the matrix with a few things switched around. We're going to change the position of our two entries along the diagonal. So this becomes -3, this becomes -1. And then we just change the sign of the entries along this diagonal. So 5 becomes -5, and -2 becomes +2. So our inverse then is going to be -3/13, -5/13, 2/13, and negative 1 over 13. So that's it. So there's our inverse. That's all we have to do for our drill problems. For a 2 by 2 matrix, finding its inverse is just as quick and as simple as this. Now, finding the inverse of a matrix in general, that is a hard problem. 3 by 3 matrices are much harder to find the inverse for. 4 by 4 and higher get to be quite difficult. We're going to look at a technique that extends as far as you need to go, but it quickly becomes pretty tedious. So we're going to see it on a 3 by 3 matrix. That's the biggest that I'll ask you to do anything for. But it's handy. It gives us a little bit of insight into what's going on when we talk about the inverse of a matrix. So let's take a look at this more complicated inverse. So if you find yourself so lucky to take a linear algebra class later in your life, a lot of what we are doing right now you will see again, and you'll see them called fancier things. You'll learn about adjoints. You'll learn about elementary matrices. We're keeping things simple here. We're just going to look at inverses and leave it at that. So this technique that we're going to look at here, it is again tedious, unfortunately. Matrices are certainly one of those tools that lend themselves very easily to our other tool of calculators and computers. Computers can crunch these things no problem. Doing them by hand is doable, though. It is, again, a little tedious, but it's good that we see how to do it so that we understand what the computers are doing, what the calculators are doing, and so that if something goes wrong, we can peek into the code and figure out what's not quite right with the programming. So here, what we're going to do, we're going to take our matrix and we're going to write what's essentially an augmented matrix. Remember when we talked about Gaussian elimination, using a matrix to solve a system of linear equations? We talked about an augmented matrix where we put on the right-hand side of this line the constants, the constant part of each of our equations. What we're going to put here this time for finding an inverse is a copy of where we're wanting to go. We are wanting the product of this matrix with the matrix that we're wanting to find to be the identity. So we're going to put a copy of the identity right here. Our goal is to use our 3 basic transformations. So our 3 basic transformations again are multiplying a row by a constant, interchanging 2 different rows, or adding one multiple of a row to another. So using those 3 tools, we want to convert the left-hand side of this big augmented matrix into the identity. What we'll be left with on the right-hand side after this process will be our inverse. So much like with Gaussian elimination, my recommendation is to proceed column by column. Get column 1 to look exactly the way you want it, then move over to column 2, get it the way you want it, then move over to column 3. So the first thing we want is we want this term to be a 1. So the easiest way I see to do that is to multiply row 1 by negative 1/3. So make a little note here what we're doing. We're multiplying row 1 by negative 1/3. We're going to put that in row 1. So when we do that, our top row becomes 1, 1, 1, because each of these are negative 3. This 1 over here becomes negative 1/3, and then the zeros remain the same. Okay, we didn't change anything else, so our other 2 rows remain exactly the same. Not a single change for these 2. 0, 0, 1. All right, so if we proceed column by column, we want to get this entry and this entry to be zeros. So what I recommend doing here is let's multiply this row by 2, add it to this row, that's going to make this a 0, and multiply this by 4, add it to this row, that's going to make that be a 0. So we can actually do both of those at the same time. So let's say 2 times row 1 plus row 2, we're going to put that in row 2, and then 4 times row 1 plus row 3, we'll put that in row 3. Okay, we'll go ahead and write row 1 again, because we're not actually doing anything to change row 1. Notice here we're only changing row 2 and row 3. So row 1 exactly the same as it was before. Okay, our new row 2. The way we're finding our new row 2 is we're taking 2 times row 1 here, adding it to row 2. That will give us our new row 2. Okay, so 2 times 1, that's 2, plus negative 2, that's going to be 0. 2 times 1, that's 2, plus 0, that's going to be 2. 2 times 1 is 2, plus negative 2, that will be 0. 2 times negative 1/3 will be negative 2/3. 2/3. And then these will both be 0. So 0 plus 1 is 1, 0 plus 0 is 0. Okay, similarly, we're going to multiply row 1 by 4 and add it to row 3. So 4 plus negative 4 will be 0. 4 plus 5 will be 9. 4 minus 3 will be 1. Negative 4/3 plus 0 will be negative 4/3. 0 plus 0 will be 0. 0 plus 1 will be 1. Okay, so notice our first column is exactly the way we want it. 1, 0, 0. So let's move on to column 2. To get column 2 the way we want it, we want this 2 to be a 1. And then we'd like for this entry and this entry to become zeros. So let's multiply row 2 by 1/2. That's going to make this a 1. So 1/2 times row 2. So row 1 and row 3 are going to be the exact same as before. So 1, 1, 1, minus 1/3, 0, 0. All right, and then 1/2 of row 2, so we get 0, 1, 0. 1/2 of negative 2/3 will be negative 1/3. 1/2 of 1 is 1/2, and then 0. And then row 3 is the same as before. 0, 9, 1, negative 4/3, 0, 1. Okay, so we've got the 1 where we want it to be. So we want this entry and this entry to be a 0. We want those to become a 0. So our standard trick is going to be to take the row that we're working with here. So we want this column to be perfect. So since the middle column, we're actually going to work with the middle row as well. We've got the 1 where we want it. So let's multiply this by negative 1 and add it to row 1, and then negative 9 and add it to row 3. So negative 1 times row 2 plus row 1. That's what we're going to use to find our new row 1. And then negative 9 times row 2 plus row 3. That will give us our new row 3. So let's see here. So 0 plus 1 will be 1. Negative 1 plus 1 will be 0. 0 plus 1 will be 1. 1/3 minus 1/3 will be 0. Minus 1/2 plus 0 will be minus 1/2. And then 0 plus 0 is 0. So row 2 itself doesn't change any. So we just copy it again. And then finally, row 3, we're going to multiply row 2 by negative 9 and add it to it. So 0 plus 0 is 0. Negative 9 plus 9, let's see here, that's going to be 0. 0 plus 1 will be 1. Negative 9 times 1/3, that's going to be, let's think of it as positive 9/3 because we're going to turn around and add negative 4/3. So 9/3 plus 9/3 minus 4/3, that will be positive 5/3. Negative 9/2 plus 0 will be negative 9/2. And then 0 plus 1 is 1. All right. Again, this is tedious, but we're almost done. Notice we've got column 1, it's still the same way. Column 1 has not changed any. Notice now, column 2 is the exact way that we want it. So lastly, we need to fix column 3 so that's the way we want. Notice we already have the 1 where we want it. So all we need to do is to make this one a 0. So the way that we will do that, let's multiply row 3 by negative 1 and add it to row 1. So negative row 3 plus row 1, that will give us our new row 1. All right, so 0 plus 1, that's 1. 0 plus 0 is 0. Negative 1 plus 1, that's going to be 0. Negative 5/3 plus 0 is negative 5/3. 9 halves minus 1/2, that will be 8 halves, so 4. And then negative 1 plus 0, that will be negative 1. And then everything else is the exact same. 0, 1, 0, negative 1/3, 1/2, 0, and 0, 0, 1, 5/3, 9 minus 9 halves, and 1. So this right here, this is our inverse. So it took us a bit of time, but we finally got it. So our inverse matrix, negative 5/3, 4, negative 1, negative 1/3, 1/2, 0, 5/3, negative 9 halves, 1. Okay, so this is pretty time intensive. This will take a little while if we're tasked with doing this, but I hope that we see the routine. I would not be surprised if we see a smaller matrix. If I ask you to use this technique for a 2x2 matrix, just to demonstrate that you understand how this generalizes. For the drill problems, once again, we will only see a 2x2 matrix. All I'm expecting you to use there is the quick technique, using 1 over the determinant and then changing the position of the A and D entries and then changing the sign of the B and C ones. But if we see something where we're asked to find the inverse on the application portion, this is the technique that I'll ask you to use. Again, it is involved. It does take some time. This is a great candidate for using a calculator to help us out. But once again, it's good to peek behind the scenes and see what's going on here.